Hello, class. We're about to get started on section 4.1, and it is entitled A Likely Story. Our learning objectives is to understand key terminology and the study of probability, to compute and interpret theoretical and empirical probabilities, and compare theoretical and empirical probability. Okay, now we look at the bottom of page 299. It says, in this lesson, we'll examine the basic concepts involved in studying probability. In short, the probability of something occurring is a number that represents how likely it is to occur. You can think of it as a percent chance of something happening. The major difference between percent chance and probability is that we will write probability as a number between 0 and 1. So in that regard, it's like percent chance with the percentage written in decimal or fractional form. Number one, it says a forecaster says that there's a 70% chance of rain today. What is the probability of rain? So remember, 70% is written as so, but now we have to rewrite this as a decimal or fractional form because we want our answer to be between 0 and 1. So 70% is the same thing as 70 over 100. And then we can simplify this to be 7/10. Or we could write this as 0.7. And we could put that in our calculator to illustrate this. So what I'm going to do, I'm going to pull up the TI calculator only because this is just basic arithmetic. And like I said, it takes up less room than our traditional Desmos calculator. So we will have 70 divided by 100, and that will give us our decimal. Now we know in Desmos we would pick, well, matter of fact, let me pull up Desmos. I guess there's no way around it. Let me see if I could get it to fit. Give me 1 second. That means I will have to, okay, with Desmos, we would do 70 divided by 100. That will give us 0.7, which is our decimal. And then we will hit this, this fraction bar here. And then it will give us our fraction as well. So that's an illustration of how Desmos would work. Okay, next. We'll move on to our next page, which is page 300. And it says here, sample spaces. Processes such as flipping a coin, rolling a die, or drawing a card from a deck are called probability experiments. A probability experiment is a process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. Some examples of a trial are flipping a coin once, rolling a single die, and drawing one card from a deck. When a coin is tossed, there are two possible outcomes, heads or tails. It says list them, so we will put heads, comma, tails. Those are the two possible outcomes. Now, number 3, it says when rolling a single die, there are blank outcomes and list them. Now, we're talking about a regular die. So there are 6 possible outcomes, and the possible outcomes are 1 through 6. Now we go to problem number 4. But let's read the directions first. It says, in a probability experiment, we can predict what outcomes are possible, but we can't predict with certainty which one will occur. We say that the outcomes occur at random. In any experiment, the set of all possible outcomes is called the sample space. What you did in question 2 and 3 was find the sample space for 2 different probability experiments. Number 4, for each experiment described below, Write the sample space. The first is filled in for you as a reminder that a sample space is a set, and we will write sets inside braces with commas separating the elements. So first of all, if we look here, you notice we have braces here. Now remember, we're in the course pack on page 300. We have braces and we have the elements. The elements of flipping a coin are head and tails, and those are the possible outcomes. Now for a die, we already answered that in problem 3. It's 1 through 6, and we separate them by commas, but to indicate they're a set, we will put that in a brace. Now it says answer a true, false question. So then you will have true, false. So this is a true, false question, and we will have our braces. Now, sometimes, of course, we know true, false questions can have a T, comma, F. So just to let you know. Now it says flip 2 coins. Now this is a little different because remember, on one coin you can have both heads. I mean, on one flip of the 2 coins, you can have both of them heads. The second, you can have a head and a tail. The third, you can have a tail and a head. And the fourth, you can have 2 tails. These are all the possible outcomes, and these are all the elements of the sample space. Now, we come here to problem number 5. Oh, one other thing. Before we go to problem 5, head, tails, and tail heads are different when it comes to probability, even though they have the same elements. They're still considered different because heads was first here, tails was second, as opposed to tails being first and heads second. Okay, so now we go here to number 5. It says, in finding probabilities, it's sometimes necessary to consider several outcomes of a probability experiment. It says number 5, for example, when a die is rolled, we may want to consider obtaining an odd number. There are blank outcomes that satisfy this criteria. List them. Now, with a die, odd numbers, we know here are 1, 3, and 5. So there are 3 outcomes. And the odd numbers are 1, 3, and 5. Now it says here, getting an odd number when rolling a die is an example of an event. Now, an event is any subset of the sample space for a probability experiment. This means that an event could be a single outcome or a set of several outcomes. Now, there's a subtle distinction between an outcome and an event. An outcome is a single occurrence, while an event can contain a number of outcomes. So rolling 2 with a single die is an outcome, but can also be considered an event. Rolling an odd number, on the other hand, is an event made of 3 outcomes, but is not itself an outcome. Let's look at that distinction more closely. You already listed out the sample space for flipping 2 coins. Look back at the table on the previous page and make sure that you have 4 outcomes in your sample space. Number 6, how many results match getting heads on the first flip and tails on the second? Now, if we went back here to this table, they said heads on the first, tails on the second. It's only 1. So it'll be, the answer to number 6 would be 1. So that's an outcome. Getting heads on the first and tails on the second, that's an outcome. Now, number 7, how many results match getting 1 head and 1 tail? They said 1 head and 1 tail. There's 1 head, 1 tail. There's 1 head, 1 tail. So it's actually 2. Because they didn't care what order it was in. As long as it's 1 head and 1 tail, that's all that matters. That's an event. So an event has more than one outcome, and the outcome only has one outcome. Okay, now, number 8. It says identify each scenario in questions 8 through 10 as an event, an outcome, or both. Now, it says when rolling 2 dice, getting 3 on the first die and 5 on the second. So, it says 2 die getting 3 on the first die and 5 on the second. That can only happen once. So that would be an outcome. And then there's also an event. It's an outcome because it only occurs once. It's an event because an event is just made up of outcomes. Okay, now it says when rolling 2 dice, getting a total of 10. Now let's take a look at how you could get a total of 10 on die. You could get a 4 and a 6. You can get a 5 and a 5. And you can also get a 6 and a 4. So this is an event. There are 3 ways to get 10 on dice. Now, number 10, when flipping a coin 10 times consecutively, getting tails 8 times. Now, you can get the first 8 could be tails. The last 8 could be tails. Or any other event that gives 8 tails. Once we have over 1, we know that this is strictly an event. Once we have over 1 outcome, we know that this is an event. Okay, now we move on. Now we have theoretical probability. Now we're ready to specifically define what is meant by probability. The first type we'll study is called theoretical probability. The goal is to determine all of the possible outcomes in a sample space and determine a probability or a likelihood of an event occurring without actually performing experiments. There's one key assumption we make in theoretical probability, that every outcome is a sample space is equally likely. For example, when a single die is rolled, we assume that each number is equally likely to come up. When a card is chosen from a deck of 52 cards, we assume that each card has the same probability of being drawn. You'd have to be awfully bored to flip a coin 100 times. But if you did, about how many times do you think it would land tail sides up? Now, if there's an equal chance, and remember, with a coin, you only have 2 outcomes. You could get heads or tails. So we would think that it would be half the time. So about 50. Now, number 12, it says, what percentage of the time would you expect the coin to land tails up? So that'll be about 50%, because it'll be 50 out of 100. I'll write that down. It'd be 50 out of 100, which is about 50%. 13, write a fraction with the number of flips in the denominator and the number of times you're expecting it to land tails up in the numerator. So that's basically what we did. We flipping it 100 times, that goes in the denominator, and we're expecting it to land tails up 50 times. And we know that that equals 50%. It says, what does this have to do with the answer to question 12? And this is from question 12. It's the same. Okay, now we have down here where it says calculating theoretical probability, but let's read what it says above it. It says, congratulations, you just computer your first theoretical probability. You didn't actually flip a coin 100 times. You just used reasoning ability to decide what the likelihood of getting tails is. That's what makes it a theoretical probability. You developed a theory by thinking as opposed to gathering data experimentally. We'll get to that in a bit. Calculating a theoretical probability. The probability of an event E is a sample space S occurring is given by, so the probability of an event is equal to the number of outcomes in E and the number of outcomes in S. Now, S is the sample space, which means the total amount that you're using. And then N is the expected outcome, the expected event. Okay, so now, questions 14 through 16, a single six-sided die is rolled. Find the probability of each event. If you need to, look back at your sample space on page 300 for reference. So basically, it says rolling a 2. Now, when we look back at that table that we had, there's only 1 2 in the sample space. So that means, first of all, with a die, we have 6 events, and it can only happen 1 time. A rolling a 2. Okay, now we go here to 15. It says rolling a number less than 5. If we go back to that table again on page 300, looking at the die, all the numbers less than 5 is 4 of them. So it'll be 4 out of 6. Now, just in case you're not good at simplifying, again, we have Desmos that you could use. You could type in 4 divided by 6, then get that as a fraction. So it'll be 2/3. Now it says roll in an odd number. Now again, we go back here. Look at the numbers. Odd numbers is 1, 2, 3. 1, 3, and 5. So the odd numbers we know are 1, 3, and 5, and we know that's 3 out of 6, which is 1/2 when it's simplified. Now, again, this isn't as bad, but let's take a look here at problem 17. It says, if 3 coins are flipped, write the sample space. Remember that tails, heads is a different outcome than head, tails, even though both result in 1 tail and 2 heads, which, by the way, sounds like a bunny rabbit. Yeah. Okay. Now, for 17, 3 coins. First of all, we have 3 heads. Then we could do 2 heads and a tail. Then we can do head, tail, head. Then we could do tail, head, head. We could do head, tail, tail. We could do tail, head, tail. We could do 2 tails and a head. And then finally 3 tails. Now, if we count this up, 1, 2, 3, 4, 5, 6, 7, 8, we have 8 different outcomes here. Now, we come down here to problem 18. It says for questions 18 to 20, 3 coins are flipped. Find the probability of each event. Now, they want to know how many of these have 2 tails. Well, let's take a look here. We have 2 tails here. That's 1. We have 2 tails here. That's 2. We have 2 tails here, which is 3. Now this has 3 tails, so we wouldn't count that. So it's 3 that has 2 tails out of 8. So it's 3 out of 8. Now, 19, it says at least 1 tail. That means it can have one tail or more. All of them have one tail or more except for the first one. So that's 7 out of 8. Now it says at most one tail. So that means it can have one tail or lower. So that would knock out this one, this one, this one, this one. Because all these have more than one tail. So these have one tail or less. So that's 4 out of 8, which we know when we put in our calculator, we simplify that to 1/2. So we have half of them that has at least one tail. I mean, at most one tail. Okay, now we move on to the next page. It says, now that we know a little bit about probability, we can make a series of simple but important observations. Okay, observation 1, probability is never negative. Explain why probability can't be negative. Because an event cannot have a negative number of possible outcomes. Now we know that the lowest that an event can happen is that it doesn't happen, which would be 0. It will not have more, it will not have less than 0. So that's why we know it's not negative. So 22, it says, explain why probabilities are never greater than 1. An event cannot happen in more ways than total possibilities. Just like this here. Let's take, remember at the start of this lesson, we talked about percentages. And then we decided that with these problems here, we would make them to decimals or fractions. We know in a percent, 100% means everything. 100% means it all. 100% means that it's guaranteed to happen. So if an event is guaranteed to happen, you can't get higher than 100%. And remember, our events go from 0 to 1. So 1 being 100%, it cannot get greater than that. Okay, 23. It says observation 3. When an event can't possibly occur, its probability is 0. When an event is certain to occur, its probability is 1. Explain why impossible events have probability 0 and certain events have probability 1. Now, impossible events are 0 because they cannot occur. Certain events must happen. So all possible outcomes will occur. Okay, problem 24. This is going to be our last problem of this section. It says, observation 4, if you add the probabilities for every outcome in the sample space, the result is always 1. Explain why the probabilities of all outcomes have to add up to 1. Thinking of rolling a die might be helpful. Okay. All outcomes would account for all possibilities. So, as we said earlier, 100% chance or 1. Okay, class, we're about to start section 4.4 now. It's called Crunching the Numbers. And it's on page 351. Our learning objectives is to explain the difference between the population and the sample, compare and contrast different sampling methods, organize data with frequency distributions, and analyze data with stem and leaf plots. Okay, first, we go down here to the bottom. It says, as we begin our study of statistics, it would seem reasonable to have a really good idea of what that actually means. Statistics is a branch of math that involves collecting, organizing, summarizing, and presenting data and drawing general conclusions from that data. If we're talking about grade inflation, then relevant data might be average grade point averages for students in several different years. The table below shows some GPA data from the website gradeinflation.com. Okay, we actually go from 1991, 92 school year to 96, 97, 2001, 2002, 2006, 2007. It looks as though all of them are about 5 years apart. In statistics, we start with the question we like to answer. Like, is grade inflation a real phenomenon? Then we gather data and try to interpret it in order to answer the question. Okay. So it says, write a verbal description of the information provided in the table. Do you think it supports the idea of grade inflation? Now, we know that GPAs, just to show this really quick here, might be kind of hard to have both here. Well, I could do this. I could slide it down. If you look here, you notice GPAs have been increasing. So we could say GPAs have been increasing every 5 years since 1991. That's one conclusion that we come up with. And then it says, but the data do not say why. We don't know why it's increasing. So we cannot say it is grade inflation, because we don't know why the grades improved. Because the grades could have improved because they could have gotten a new curriculum. We don't know. So now, we'll move on here to problem number 2. It says, how do you think these numbers were calculated? What students' GPAs were considered? Discuss. Now, this is more of an opinion piece, but I'll put this down here anyway. It is likely that not all undergrads in the U.S. were considered. they probably chose some schools and asked them for GPA data. Okay, now it talks about here the ideal way to gather GPA data would be to add the GPAs of every college student in America during each year, then divide by the number of students. Needless to say, that's not particularly realistic. Aside from legal ramifications, in any given year, there are more than 20 million students enrolled in American colleges. And by the time all of that GPA data were gathered and recorded, many of them would be contemplating retirement. Instead, GPA data is obtained from a sample of college students. Okay, now, it says here, population consists of all subjects under study. A sample is a representative subgroup or a subset of a population. So that's very important. Because in a lot of things in statistics, you're going to use samples. Okay, now, in the case of the GPA data we've been studying, the population is every college student. The sample is the group of students we actually recorded GPAs for. It says, in this case, GPA data from a sample of 70 different colleges were used to compute the average. The thing that makes the data compelling is that the sample is representative of the population as a whole. The schools chosen vary in size, cost, and geographical location. Some are public, some are private. Discuss what exactly is meant by a representative sample and why it's so important in answering questions using statistics. A representative sample is a smaller group that will likely provide a similar mix of results to the entire population. Without it, your results won't reflect the population and they will be worthless. All right. So basically what this is saying is if you do not get a representative population, then your data is not really going to be helpful to anyone. Because basically if you get them all from the same group, I mean, that's not going to really give you an indication of the general GPAs out here. Okay, now sampling methods. We will study 4 basic sampling methods that can be used to obtain a representative sample: random, systematic, stratified, and cluster. In order to obtain a random sample, every subject of the population has to have an equal chance of being selected. The best way to obtain a random sample is to use a list of random numbers. These can be generated from a variety of internet sources or from a computer or calculator. Subjects in the population are numbered, and then the ones to be studied are picked by using a corresponding random number. Okay, number 6. If you were going to do a survey with every student at your campus as the population, describe how you might obtain a random sample to survey. More specific is better. So we will use a computer to randomly choose from a list of student ID numbers. That'll be very random. Now, a systematic sample is taken by numbering each member of the population and then selecting every kth member, where k is some natural number. For example, the researcher from gradeinflation.com might have numbered all the colleges willing to release grade information and chosen every 10th one. In this case, k equals 10. When using systematic sampling, it's important that the starting number is chosen randomly. Let's get back to the campus survey mentioned in question 6. Describe how you might develop a systematic sample. We can look at an alphabetical list of all students and choose every 100th name. Okay, when a population is divided into groups, where the members of each group have similar characteristics, like large public schools, large private schools, small public schools, and small private schools, and a certain number of members from each group are chosen at random, the result is called a stratified sample. For example, the grade inflation researcher might have decided to choose 5 schools from each of those groups. Medical researchers often stratify samples by dividing subjects into gender groups, age groups, racial groups, or many other categories. They would then choose a similar number of subjects from each group to compose the stratified sample. Okay, now number 8, it says describe how you put together a stratified sample for that campus survey we've been talking about. So we could split the students up by class level. You know, we have freshman, sophomore, etc. And randomly choose a group of students from each. It says when an existing group of subjects that represent the population is used for a sample, it is called a cluster sample. For example, an inspector might pick at random 1 carton of laptops from a large shipment and test each one to see how many are defective. The group in this carton represents a cluster. In this case, the researcher assumes that the laptops in the carton represent the population of all laptops manufactured by the company. In the case of the grade inflation survey, researchers might have looked for an existing organization that many colleges of different types already belong to, then use contact information from that organization to reach out to the schools. It says here, describe how you might develop a cluster sample for our campus survey. Okay. We could split up or split the students up by major. And then randomly choose a few majors and survey everyone in those majors. Now think about 4 different sampling methods the researcher from gradeinflation.com could have used. For questions 10 through 13, write which of the sampling methods we've studied was used for each situation. Explain your choice. Okay. For number 10, the researcher randomly selected 3 states and then asked all colleges willing to release grade information from those states. Now, of course, they said 3 states. We have 50 states. So that would be a cluster. There's 3 states. The cluster are the states. And we gather data from all possible schools in the selected states. Number 11, the researcher numbered all of the colleges willing to release grade information and chose every 10th one. Now we know that's systematic. That's the one with that case. So we chose every 10th. All right. Now we go here to problem 12. The researcher numbered all of the colleges willing to release grade information and chose several of them using a random number generator. So it'll be random. Every school has an equal chance of being chosen. Number 13, it says the researcher grouped the schools by 2-year state schools, 4-year state schools, 2-year private schools, and 4-year private schools. The researcher then decided to choose 5 schools from each of these groups. So this would be stratified. Or stratified, I should say. So there's a few chosen from every category. Now, number 14, it says rank the 4 sampling methods in questions 10 through 13 from best to worst in terms of how representative you think the sample would be. Explain your rankings. Okay, now remember, this is up to an opinion here. So I would say first stratified, and then make sure all type of schools are represented. The next would be random samples. Avoid accidental bias. Okay, 3. I will go with systematic. Still likely to be a fairly good mix. And finally, number 4 would be cluster. Cluster will be the last because it seems unwise to leave out whole states. Because remember, we only did, I think it was 3 states. So that didn't seem that wise to leave out a whole state. Okay, now we need to move on here. We have frequency distribution. Now, it says here the data collected for a statistical study are called raw data. Raw data can be really difficult to interpret. In order to describe situations and draw conclusions, we need to organize the data in a meaningful way. 2 methods that we will use are frequency distributions and stem and leaf plots. First up, we'll study categorical frequency distributions, which are a way to organize data that are divided into distinct categories, like gender, your class standing in school, or conferences for college football teams. A categorical frequency distribution is a table in which you list different categories. Then count up how many individuals in a sample or population fall into each category and list those frequencies. In questions 1 and 2, you will create a categorical frequency distribution. Number 1, 25 volunteers for a medical research study were given a blood test to obtain their blood types. The data are shown below. What would the categories for the data be and why? Okay, it would be the blood types. And that's because the results can be categorized. Okay, now we get to number 2. It says, build a categorical frequency distribution by writing in your categories, then putting tally marks in the second column as you count the number of individuals in each category. So first thing we want to do is list the different blood types. We have A, B, AB, and also O. Now, if you look here at A, if we count them up, there are 5 A types here. Then there's 7 B types. Then there are 4 AB types. And finally, there are 9 O types. Now it says here, use your distribution to write some conclusion on blood types in the population. Do you think there's enough data for your conclusions to be reliable? Okay, listen, first of all, if we count how many we have here, what's this, 25? You cannot base world blood types on 25 people. Okay. But we can conclude the most frequent blood type is O. And the least common is AB. But remember, it's like, I think it's close to 7 billion people, if not over that. So we cannot trust 25 people to account for 7 billion. That's that would be a little much there. Okay, now it says another type of frequency distribution that can be constructed using numerical data, and it's called a group frequency distribution. In a group frequency distribution, the numerical data are divided into classes. For example, if you gather data on the weights of people in your class, there's a decent chance that no two people have the exact same weight. In that case, everyone will be in a separate category, and each category will have one weight in it. This, of course, would make the frequency distribution no more useful than the original list of raw data. So it would be reasonable to group people into weight ranges like 100 to 119 pounds, 100 to 139 pounds, and so forth. In the 100 to 119 pound class, we call 100 the lower limit and 119 the upper limit. So number 4, with these ranges, where would we put someone that weighs 119.8 pounds? It'd be nowhere, because that is in between classes. It'll be nowhere. As question 4 illustrates, the way we choose classes is dependent on how the data values are rounded. The weight classes we chose above would be fine if all the weights are rounded to the nearest pound. But if weights were rounded to the 10th of a pound, we want to make the classes 100 to 119.9, 120 to 120.9, and so on. Now it says constructing a group frequency distribution. Now this is very important, especially when you're making your note sheet. So it says here, decide how many classes you want to divide the data into. Between 5 and 15 is acceptable. So we want the data to be divided no lower than 5 classes, but no more than 15. All right, now determine the width of the class. Now the class width is the largest data value minus the smallest data value divided by the number of classes. Now we'll get to that. Then it says, then round this value up to the next biggest whole number. So even if you have 5.01, you still would go up to 6. It's not typical rounding. You just go up to the next biggest whole number. Now, step 3, use the lowest number in the data set or a nice number lower than the number for the lower limit of the first class. Add the class width to the first lower limit to get the second lower limit. Do this for all classes. Find the upper class limit for each class by subtracting 1 from each lower class limit, and then tally up the number of data values in each class. Then put the frequencies next to each class in the table. Now, we're going to go through all of that. So, we go here. It says we'll illustrate by organizing the following data, which are the record high temperatures for each of the 50 states in degrees Fahrenheit. Okay, now, why would a categorical frequency distribution be a bad idea for this data? Okay. And the reason being is categories would be each different temperature. It'd be way too many. Now you may have one or two that's the same here, but let's just say if you had three that were the same, that still would be about what, 47 different temperatures that you have to categorize, and that is way too many. Okay, now, number 6, it says, how far apart are the largest and smallest values in the data set? Okay, so we will take the largest minus the smallest. The largest would be 134, and the smallest would be 100. So it'd be 34. Now, number 7, it says, how wide would this make each class if we went with 15 classes? Does this sound like a good idea? Now, remember, back on the previous page, we broke this up into parts. The class width is the largest data value minus the smallest data value, and then we would divide that by the number of classes. So we already have the largest minus the smallest, which is 34, and we want 15 classes, which would come out to be about 2.3. Now, that will lead us to 3 as our class width. Now it says, does this sound like a good idea? This would go too far past our largest value. So this would be a bad idea. And let me show you why it would do that. Okay, if we have 15 classes, remember the class width is 3. So we have 15 classes times 3. That means that it would go to 45 numbers here. And we're trying to get to 34 numbers. So that would be too far out. That would be too far out as far as the class width is concerned. Now, again, like I said, you'll get a better understanding as we continue to go through this. Okay, number 8. I think 7 classes seem like a really good idea for this data. What do you think if I choose 7? So now, 7 divides evenly into 35, which is very close to 34. So I think that would be a good one. So now, for number 9, divide the range of values you found in question 6 by the number of classes we chose. So it's 34 divided by 7, which would be about 4.9, which would be 5 class width. So that means we should only go about 1 over that amount of our highest amount, because the width is up to 34. Okay, now we come down here to number 10. Why is the smallest value in the data set a very good choice for the lower limit of the first class in this case? Well, our smallest value is 100, which is a nice starting number. Now, if it would have been 101 or 97 or something like that, we probably would have to second guess ourselves. But 100 is pretty good. Now it says, starting with the lower limit, it says find the lower limit for all the other class. It says starting with the lower limit we chose in the last question. Keep adding the class width you found in question 9, recording each result to make a list of the lower limit for each of the 7 classes. So first of all, we're going to do 7 classes. So we start off with 100. That is our lower limit. So our class width is 5, which we found in problem number 9. So we'll keep adding 5 until we get a total of 7 class. So it'll be 105, 110, 115, 120, 125, 130. And I ran out of space, but it'll be 135 would be, it'll go from 100, 1, 2, 3, 4, 5, 6. Oh, I was supposed to stop at 130. Okay, so it's supposed to go from 100 to 130. Those are the lower limits. Okay, now, number 12. It says subtract 1 from each lower class limit you found in question 11. Get the upper class limit from the previous class. For example, the first 2 classes in the group frequency distribution are 50 and 58. The upper limit for the first class would be 57. Remember, if a data set contains number with decimal parts, we adjust the upper limits to reflect that. For example, the values in the data set are rounded to 2 decimal places, and the class limit is 2. The upper class limit would be 1.99. So we don't have to worry about that right now. So this is what I want to do. I want you to see both. So let's first write the lower limit. Let's rewrite what we have for the lower limit. Okay, that's the lower limit. Now the upper limit. Now remember, the upper limit will go with the matching lower limit. So we'll take 1 from this lower limit. So this would be 104. We'll take 1 from this 110. This would be 109. Now listen, just to tell you all this here, you don't have to keep subtracting 1. What you could do is once you get that first upper limit, you can add the class width to it, just like you did with the lower limit. So this would be 114, 119, 124, 129, and 134. So it's the same process. Once you get the lower limit, once you get the upper limit, all you have to do is add the class width to it. And it will give you the answers. Okay, now we move on here to problem 13. It says, fill in the table below using the class limits you decided in question 11 and 12. All right. So remember, we had 100 to 104. We had, I guess I'll do it like this. Let's just write all of them. All the lower limits, then all the upper limits. Now this dash tells you how far it goes to. So this would be 109, 114, 119, 124, 129, 134. Now they want us to tally all of this up. So what we would do is this here. I'm just going to give you the answers here. So it should be 3 here. This would be 8. Then this would be 16. And this would be 13. Then we will have 7. Then we will have 2. Then we will have 1. Now, when you add all of your frequencies together, it should equal to how many elements you had in here. In this case, it'll be the 50 states. So this should equal 50. So this would be 2730, 2740, and that will end up being 50. So 14, it says write down at least 3 observations you can make from analyzing your frequency distribution. Okay, first of all, the obvious. the majority of states are in the temperature range of, what's that, 110 to 114? All right. (110 to 114). Then we can say the lowest amount of states have a temperature range of 130 degrees to 134 degrees. And then if you notice here, if you look basically here in the center, you know, most of them resides in the 110 to 114, 115 to 119. They're very close. But as you go higher or lower, you notice that the frequency gets lower. So basically, as temperature decrease or increase, the frequencies decrease as well. Now, of course, there are other things that you can see here as well, but as long as it's consistent with the data, it's fine. All right. Now we come here to the back. We have what we call stem and leaf plots. It says another way to organize data is to use stem and leaf plot, sometimes called a stem plot. Each data value or number is separated into two parts. For a two-digit number such as 53, the tens digit 5 is called the stem, and the ones digit 3 is called its leaf. For the number 72, the stem is 7 and the leaf is 2. For a three-digit number, say 138, the first two digits 13 are used as the stem, and the third digit 8 is used as the leaf. For values rounded to the tenth place, like 8.4, you can use the value to the left of the decimal point as the stem and the tenth place as the leaf. As in our next example, in any case, the very last digit is used as the leaf, and what comes before it is the stem. Note that we'll include a key with our plot that clarifies what the stems and leaves represent. Okay, the data below are the July 2015 unemployment rates for each state. All right. So now it says if you were to build a group frequency distribution, what classes would you choose? All right, so if we look here, our lowest value is 2.8. And our highest value at West Virginia is 7.6. So if I looked at this here, I probably would do a class of 5 because they're not that much different from each other. So if you look here, I probably would do maybe, because they're asking for a guess here. So I'd maybe do 2.8 to 3.7, 3.8 to 4.7, had them about 1 apart, 4.8 to 5.7, 5.8 to 6.7, and then 6.8 to 7.7. So that would be 5 classes, which fits into that 5 to 15 we talked about earlier. Now, 16. What will you choose to be the stems for the data? Okay, if you notice, all of these have only 1 digit in front of the decimal, 1 digit behind the decimal. So it'll be the ones digits. The ones digit. Okay, what will you choose to be the leads for the data? It'll be the tenth place. So it'll be the ones digits for the stem and the tenths place. Now we know this is all leading up to something. So now we come down here to 18. It says, list all whole number parts that appear in the unemployment data. That is the digits to the left of the decimal place. You don't need to repeat them if they appear more than once. So these ones digit will be from 2 through 7. If you look there at this table here, you notice in front of the decimal, the lowest number is 2, the highest number is 7, and it includes all the ones in between, all the numbers in between. Okay, now we go here to 19. It says, write your answers from question 18 in order under stems in the table below. Write the lowest values first, then larger values as you work your way downward. Okay, so for 19, we'll write 2, 3, 4, 5, 6, and 7. Now it tells you here, the key tells you here, this 6/2, the 6 is the stem, the 2 is the leaf, means 6.2. So now, here comes a critical part here. And I'm going to tell you this. I'm just going to give you the answer because that is a lot of data to try and go through right now. The leaves are all, if we look at all the numbers that are 2s, and I'm going to show you this here, all the numbers that have the 1's place as a 2. So we will go here. We have this 2.8, and it should be another one here. And we had 2.9. These are only 2 values that have 2 in a 1's place. You know, it's 2.8 and 2.9. So we'll write 8 and 9 here. Now, one thing I want to stress here when you're doing stem and leaf, there are no commas when you do the leaves. Leaves are automatically assumed to be 1 digit. So you do not need commas there. And it will be marked incorrect if you write commas. So remember, you just write the digits as a single. Now the stems can be any length, but the leaves are always just 1 digit. So this would be 5, 6, 6, and then 3 7s for the 3s. So that's the same as saying 3.5, 3.6, 3.6, 3.7, and so on. Now 4, you add 2 zeros, 2 1s, 2 2s, 3 5s, 3 6s, 2 7s, and a 9. The 5, you add 2 1s, 2 2s, 3 3s, 2 4s, 3 6s, 2 7s, and 2 9s. 6, we add 2 zeros, 2 1s, a 2, 2 3s, 6, 7, and 8. And then finally 7, you have a 6 here. 21. Write at least 3 observations you can make about the unemployment data from looking at your stem and leaf plot. First, we could say the largest number of states have unemployment rates in the 4.0 to 5.9 range. Now, what happened was this here, they combined both of these. When you combine both of these, they have much larger values than all the rest. So from 4.9 to 5.9, that has the largest number of states have that as the unemployment rates. Now, if you take those 2 categories using these 2 categories, as unemployment rates go up or down, fewer states have those rates. Okay. And then finally, unemployment rates of 2 or 7 are unusual. Because if you notice, with 2 is only like 2.8 and 2.9. And then I should put 2s and 7s, because they're actually not just 2 or 7. So it's the 2s or the 7s, and they are unusual. Because there's only 1 in the 7s, and there's only 2 in the 2s. Okay, so now move here to 22. It says deciding on stem and leaves for the unemployment data was fairly simple because there was a natural choice of stems, the whole number of parts of each rate. They gave us a reasonable number of them, 6. That's not always the case. For the high temperature data earlier in this lesson, the natural choice of stem was seen to be the first 2 digits. But here's what the stem and leaf plot would look like in that case. If you notice here, we only have basically four classes here, or 4 stems. And we know that is a lot of data. Now, 22, it says, explain why this stem and leaf plot isn't really very helpful in organizing the data. First of all, there are not enough categories. For the stems. It is hard to tell how the values are distributed. Also, the leaves are not in order. And that's one thing I forgot to tell you too. Whenever you're writing out your leaves should be in numerical order. So I'm glad that came up now. It should be in numerical order. Okay, now, it says, in general, it's a good idea to choose stems so that there are between 5 and 15 categories. In the case of the high temperature data, we get a better organization if we divided the categories in half, so that the first category covers 100 to 104, the second 105 to 109, and so on. To signify this, we can use the symbol 10, 0 to represent a stem of 10 with leaves that are digits from 0 to 4, and 10 parentheses 5 to represent a stem of 10 with leaves that are digits from 5 to 9. In that case, this is what the high temperature stem and leaf plot would look like. Now remember, these are not exponents in these parentheses. That's just signifying that this is from 10, from 100 to 104, 105 to 109, and so on. Now it says describe why this stem and leaf plot makes it easier to analyze the organized data. Okay. The leaves are still aren't in order, but with more categories, it is easier to see how the values split up. Now 24 says, compare group frequency distributions and stem and leaf plots. How are they similar? Which do you think makes it easier to analyze a set of data? Okay. They are similar because they both show how the values are distributed when they are broken up into categories. The stem and leaf plot offers a little more information. For analyzing data. Both show which categories are most and least common. But the stem and leaf plot also retains the individual data values. So you can see every last data value with the stem and leaf plot. Okay, now we're going to move on here. And we need to go to page 368. Well, actually, let's go to page 367. Okay, really what I want to do with this page, I'm really trying to get you all to see what a histogram is. Let's see. There's quite a bit of data here. I'm going to take the liberty of filling this data out. Give me just a second here. I want to make sure that we get all of this data together. All right. So number 4, it says the National Insurance Crime Bureau reported that these data represent the number of registered vehicles per car stolen for 35 selected cities in the United States. For example, in Miami, one automobile is stolen for every 38 registered vehicles in the city. The data have been rounded to the nearest whole number. Okay, now we do a stem leaf plot here. We had 3, 4, 5, 6, 7, 8, 9. If we look at these digits here, we will go from 3 to 9. So it's 1, 3, 1, 4. So it's 38, 41. The 5s, it'll be 2, 0, 2, 3, 3, 6, 8, 9. The 6 will be 6, 8, 9, 9. 7 would be 2 zeros, 3, 4, 5, 8. 8 would be 0, 1, 3, 3, 57999. Then 9 would be 024. Now we could write a little key off to the side. The key, we could say 3/8 means 38, just to give us a perspective here. Okay, now we'll move on here to B on the next page. It says build a group frequency distribution for the data where the classes correspond to the STEM that you chose. Okay, so if you look back here at the STEM, we go basically here from 38 to 94. Now again, we want classes from about 5 to 15. Now, if we take 94 minus 38, let's take a look at this before we do any subtraction. 94 minus 38, that would give us approximately what? Well, give us exactly 56. Now, I would think with a problem like this here, I would think that 7 classes would be good. Yeah, because of our width here. 7 classes, our width would be 8. But remember, we have to go up to the next highest whole number, which would be 9. So now we could do our classes here, our frequency distribution. We could do register vehicles. I didn't leave enough room here, but it should be cars stolen as well. Registered vehicles and cars stolen, and then our frequency. All right, so we could start with 30. 30 to 39 be 1. 40 to 49, which would be 1. Because remember, well, actually, hold on. 7. Should be actually 30 to 38. Okay, let me redo this. So we do 30 to 38. And then this would be 39. Then we'll keep adding 9s. This would be 48. What's that? 57. 9, that'll be 66. And then we will have 75 and then 84. Wait a minute. 9, 48, 57, 66, 75, 84. All right. So we have 30 to 38, 39 through 47. So we'll keep adding 9 here. This would give us, what's that? 47 and 9 would be 56, 65, 74, 83, 92. Okay. I am slightly off here. So let me go back here with this. Let's just, let me see, 98 minus 38, let me see, is 56. So basically here, when they ask us to build a group frequency distribution, if we go by 9, 9 is not going to work because 56 divided by 7 gave us 8. Okay, now 9 could work if I would have started with like 31, but I started with 30. So if you notice here, it went all the way to 92. So what I'm going to do here, I'm going to go up here to the top because this was a little error here. And I notice here, we're going to have to start with 31 instead of 30. So we start with 31 and go by 9s. This would be 40, 49, Could be 58, 67, 76, and then this would be 85. This would be 39, 48, 57, 66, 75, 84, and then 93. So this actually captures it perfectly. So this would be our registered vehicles, and then cars stolen. Then over here would be our frequency. Okay, so for 31 through 39, it'll be 1. 40 through 48, we will have to. Okay, so then we will have 40 through 48, which would be 1. 49 through 57 would be 6. 58 to 66 would be 3. 67 through 75, which would be 8. 76 to 84, 1, 2, 3, to be 8. And then 85 through 90 should be 93. 85 through 93 would give us 85 through 93 would give us 8. All right. Now we move on from here. And what we do next, we go down here to our histogram, which is C. It says a histogram is very much like a bar graph that represents the information and the frequency distribution. There are two main differences between the typical bar graph and the histogram. First, the width of the bars has meaning and is representative of the class width. Second, the bars are drawn right next to each other with no space in between. Create a histogram from the group frequency distribution above. Okay. Now, this is the main thing we were coming here for, but I had to get all of the previous information. So basically what we're going to do, we're going to graph this information here. So now this is slightly off here with this here, because this information, for some reason, they were using tens. So we could just make a couple little changes here. So this would be 31 through 39. This would be 40 through, 48. And then 49 through 59. Or 49 through 57. So it doesn't look like that's going to fit. So what I would need to do here is this here. I'm just going to, okay, class, picking up from 4A, we're going to look at 4B here. It says build a group frequency distribution for the data where the classes correspond to the stems that you chose. Okay, now if we look at the stems here from the previous page, if you notice here, we have 1, 2, 3, 4, 5, 6, 7 stems. So we could just use the 7 classes. And you notice here that they go anywhere from 0 to 9 to end the classes. So we could do everything by tens here. So we don't have to go through that whole process of finding the width and the length of the class. So what we could do, we could just draw our frequency distribution here. So it'll be registered vehicles slash car stolen. And then we can have frequency. All right, so we had 30 through 39, 40 through 49, 50 through 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. The frequencies will be 1, 1, 8, 4, 6, 12, and 3. All right, and you can easily see those frequencies from the stem and leaf plot here. If you look here, you could just count how many leaves you have, and that would tell you the frequency for each. All right, now we want to move on to the histogram. And this was the main reason why we were doing this page. So we're actually going to stop at C. So now with the histogram, it says a histogram is very much like a bar graph that represents the information in the frequency distribution. There are two main differences between the typical bar graph and a histogram. First, the width of the bars has meaning and is representative of the class width. Second, the bars are drawn right next to each other with no space in between. Create a histogram from the group frequency distribution above. So we're using our information from above, and you notice here that our charts, our graph is set up the x-axis and the y-axis. So we have the class and we have the frequency. So we know from 30 to 39 is just 1. So if you notice here, it goes from 0 to 2, so that's the halfway point. So we would start here from the 0 to the 39. That is 1. 40 to 49 is also 1. Now 50 to 59 is 8. So we'll go up to 8 and make sure we cover the 50 to 59. Now the 60 to 69 is actually 4. So we'll go up to 4, and that'll cover the 60 to 69. Then the 70 to 79 is 6. 80 to 89 is 12. We'll go up here to 12. Then finally, 90 to 99 is 3. So it'll be in between the 2 and 4. And then typically we would shade in these spaces too. Now I'm not going to shade them all the way in because I don't want to use up all my ink. But this is how we would do the histogram. If you notice, they're all connected and they have specific value here. So this is basically your introduction to a histogram. This is, and it's different than a bar graph because remember the bar graph, the values are separated from each other. And we are done.